Gears, they're kind of the hidden heart of almost everything that moves, right? From our cars to massive factory machines. We really don't think about them much, but making one that's both strong and super precise, well, that's an incredible feat of engineering. So let's dive right in and see how it's done.
All right, just look at this thing, a modern car transmission. It's like this complex dance of dozens of gears, all having to work together perfectly to get power where it needs to go, smoothly and efficiently. And the thing is, even the tiniest flaw, I'm talking microscopic, could cause noise, wear, or, catastrophic failure. So how on earth do you turn a simple hunk of steel into something this precise and this durable?
So here's the game plan for this explainer. We're going to follow that whole journey. We'll start with why gears are so important in the first place. Then we'll see how they're cut from steel and how they go through a trial by fire to get strong. We'll also cover the big enemy, distortion. And finally, we'll look at that final search for perfection and wrap it all up with 3 key lessons. Okay, first up, let's just set the stage a bit. Why is this whole process so obsessively detailed?
So a gear's job seems simple, right? Just transmit power. But it has to do it perfectly, thousands of times a minute for years and years. Think about it. Tiny imperfections in a tooth's shape. That's going to cause vibration and noise. A surface that's too soft. It'll just wear down in no time. And a flaw deep inside the gear's core, well, that could lead to a fatigue failure that literally shatters the whole thing. So the key takeaway here is that precision isn't just a nice to have. It's an absolute must.
All right, so where does this all start? Well, the journey begins with a simple, kind of soft piece of steel. They call it a gear blank. And the first job is to give it that classic gear shape. So here's the basic roadmap for the whole process. First, you've got turning, which is just getting the blank to the right size. Then comes the really important part, cutting the gear teeth. Sometimes there's an optional shaving step to smooth things out. After that, it's off to heat treatment to make it strong. And finally, for those super high precision gears, you have the finishing touches like hard turning and grinding. Now, when you're talking about mass production, the real workhorse for cutting gears is a machine like this one. It's called a gear hobber, and it's designed to do one thing, and do it really, really well. Cut gear teeth quickly and exactly the same way, every single time.
The way this works is actually pretty fascinating. The cutting tool itself is called a hob, and it kind of looks like a big threaded screw. It spins in perfect sync with the gear blank, and as that hob moves across the blank, its cutting edges just sort of progressively carve out that complex tooth shape. It's this continuous, super efficient process, and that's exactly why it's a favorite for mass production.
But, and this is a big but, there's a catch. Hobbing gives you the basic shape, but the finish isn't perfect. As this review from MHI points out, it leaves behind these tiny little tool marks on the teeth. I mean, we're talking just tens of microns thick, but that's still enough to cause noise and vibration. And even more importantly, the gear is still soft. It's got the right shape, sure, but it has absolutely none of the strength it needs to actually do its job.
And that brings us to what is easily the most dramatic and transformative part of the whole process: heat treatment. This is literally where the gear goes through a trial by fire to get its incredible strength.
Okay, so there are basically 2 main paths you can take here. One is called neutral hardening, and that just makes the entire gear hard all the way through. But for the really tough jobs, like in a transmission, manufacturers almost always go with case hardening. This really is the best of both worlds. You get this super hard, wear-resistant outer shell, the case, that protects a softer, tougher core. That core can then absorb shock without shattering. So, how do they do that? Well, the most common method is a process called carburizing. You take the gear, you heat it up in a furnace that has this special carbon-rich atmosphere. And at those high temperatures, carbon atoms from the atmosphere literally soak into the surface of the steel. It's a process called diffusion. This completely changes the chemistry of the gear's outer layer. It basically turns it into high-carbon steel, which can get way harder than the low-carbon steel left in the core. And this is just a brilliant illustration of the result. Over on the left, you're seeing a microscopic view of that hardened outer case. But the real magic, the real secret sauce, is invisible. That's what's shown on the right. When they rapidly cool the gear, a process called quenching, that new high-carbon case tries to expand. This creates these powerful compressive stresses right at the surface. It's like the surface is constantly being squeezed, which makes it incredibly tough for tiny fatigue cracks to even start. That right there, that's the secret to a gear that lasts a long, long time. But of course, this incredible transformation comes with a massive risk.
As the folks at Thermal Processing Magazine say, you just can't talk about heat treating gears without talking about its biggest, most unwanted side effect: distortion.
Yeah, the very same process that gives the gear all that strength is also threatening to completely ruin its perfect shape. This is really the central battle in all of gear manufacturing. So why does the gear warp? Well, it really comes down to three main things. First, you've got stresses left over from when the gear was first cut. When you heat it up, those stresses are released. Second, at really high temperatures, steel gets weaker, and it can actually start to sag under its own weight. They call that creep. But the biggest problem, by far, is the rapid cooling, the quenching. As the steel's internal crystal structure changes to become hard, it physically expands. And if that expansion doesn't happen perfectly evenly, the gear twists and distorts.
So how do engineers fight back against this? Well, one of the cleverest methods is called press quenching. Instead of just dunking the hot gear into a tank of oil, they place it inside a special die. This die physically clamps down on the gear, holding it in shape with a ton of pressure, while carefully aimed jets of oil cool it down. It's basically a way of forcing the gear to stay straight while it's going through that really violent transformation on the inside.
But even with clever techniques like press quenching, some tiny distortions can still sneak through. And to meet the crazy high standards we have today, the gear has to go into its final stage, the search for absolute perfection.
So the modern way of doing things is to do all the final finishing touches after the gear is already hard. This lets manufacturers use processes like grinding or honing on the tooth surfaces to correct any last little bits of distortion from the heat treatment. Now, it's a lot harder to machine a surface that's already hardened, but the payoff is a much, much more accurate gear in the end. But you probably guessed it, this final step has its own hidden danger, and it's called grinding burn. If the grinding creates too much heat, it can actually damage the heat treatment on a super thin layer of the surface. It's invisible thermal damage, and what it does is it softens the steel, and, even worse, it creates these really bad tensile stresses. This can just demolish the gear's lifespan, totally undoing all the good work from the carburizing process. So, finding this invisible threat takes some pretty serious tech. The old school way, called nidal etching, literally involved dipping the gear in acid. I mean, it was messy, unreliable, and definitely not good for the environment. Today, thankfully, manufacturers use advanced methods that don't destroy the part. You've got X-ray diffraction, which can measure stress, but it's pretty slow. A really top-tier method these days is called Barkhausen noise analysis, or BNA. The great thing about it is that it's objective, it's reliable, it's fast, and it's clean. That makes it perfect for checking every single critical gear coming off a production line.
Okay, so after following this whole journey from a simple piece of steel all the way to a finished, high-performance part, what are the big lessons here? What should we really take away from all this?
Well, I think it really boils down to three main things. First off, this whole process is a balancing act. Every single step is a constant trade-off between making the gear stronger and the risk of messing up its perfect shape. Second, the surface is everything. A gear's entire life depends on what's happening in just the outer few thousandths of an inch: its hardness, its finish, and most of all, those critical compressive stresses. And finally, the biggest challenges are all about controlling the invisible stuff: the flow of heat, the movement of atoms, and those massive internal forces that can either make the gear or break it. When you really think about it, it's an incredible amount of science and control all packed into a part that most of us just completely take for granted. And that kind of leaves us with one final thought, right? What other simple things that we use every day are hiding this same level of mind-boggling, engineered complexity